And that way I post them on the RF Transmissions website and give you a copy of the recording in your chat. So if there's anything, oh gosh, encoding overload and can, okay. Might have a problem with recording this now according to this. Okay, my settings are good. I think just Discord just took a glitch. Alright, we have homework that we're going to go over, and you also have labs. And the reason why I like to cram in from 1 alpha to 2 alpha is because you're going to go over the NSM 50 starting on Monday, and if I'm not mistaken, Monday and Tuesday, you telework Wednesday and Thursday. Am I correct in saying that?
Yes, sir. And if you'll check your messages, I sent you the schedule. I couldn't combine the files, so they're
that's fine.
4 pages, but that's the schedule.
All right. All right. Yeah, I see it now. Thank you. I really appreciate that.
Yes, sir. Sorry about the multiple files. My scanner wouldn't do multiples, so I had to do it individual.
It's fine. Hey, I just love it when you provide me the information, whether it's on Discord, via, I've seen it where phones can do it, take a picture and download it on their phone, because you can get Discord for your phone. I'm not very good with mine either. I like to do mine on the major computer here. So I got a lot of files that I transfer back and forth between the AFNIC computer and this one. And the whole idea behind what we're doing today is going through the information. If you are having trouble understanding it, please stop me, because I'm going to be going fast up until the point where I see a lot of the problems with students understanding the material, because it is complicated in certain areas. Most other areas is you're looking at definitions, you're looking at description, basic facts, you name it, it's going to be there straight out of the study guide workbook. So without further ado, let's take a look at Objective 1 Alpha. Anybody got any questions for me for right now? And how we're going to work this? Because today is Objectives 1 through 2 Alpha. I'm going to get to a point, let you break for lunch, a couple hours, and then come back at 1 and finish up. Then, is it Wednesday and Thursday, or is it Tuesday and Thursday? I can't even remember 10 minutes ago.
It's Tuesday for the first set of labs, and so no, it's day 7, sorry. So, yes, Monday is that, Tuesday and
Wednesday
are
the telework days. That's where the bulk of the information from 3 alpha to 5 alpha will be given out over a period of 2 days. Most of those are going to take about an hour and a half in each session. And then when you guys are starting to do your TISR labs, we'll try to pick a time where you're all completed, and we'll go through the rest of the homework, and we'll go through the appraisals, and then I'll do a review the day before you take the tests. So that way you're well prepared, and if anybody needs any extra help, you need to voice your concerns at that point, and I will do my best to assist you. This is the toughest block in the course. I don't know.
We've heard that about at least 2 other blocks already. So
yeah, it is tough. This test, to me, resembles a true college course test. It makes you think, and if you didn't come prepared to take the test, then you're going to do poor on it. Now, the idea behind this is to get you guys up to that standard, because I just saw your grades when Sergeant Kennan had asked me that, if I had the updated grades. Again, I apologize. The instructor you guys had for The testing did not put them in, so I'm at their discretion. All I did was put into the ISs, hey, is there a possibility we could get the grades put in now, because they're asking for their averages. So we'll see. I'm thinking probably this afternoon I'll be able to have access to them if they've updated them. So that's where we stand on the grading. Any questions? Comments? Complaints? Oh, customer service department just closed. All right, we're looking at Objective 1 Alpha, identify basic facts about timing and synchronization. This is important throughout our Air Force genre, I guess you could say, because we always deal with everybody being on time. When I mean on time, you got to be at your appointment, you want to be 15 minutes early so you're on time. If you're getting there right at the appointment time, they always tell you you're late. So the object is you always want to build in some extra time in there so you arrive on time. Now you're going to be touching just about anything and everything, not only your time to go to certain appointments, but on the equipment itself is built off of timing. You guys have been playing with time ever since you walked into Jones Hall. And what do you mean by that? Well, most of our equipment has some sort of timing in it. Didn't know that, did you? But that is true. Our frequencies are built off of time. In other words, we got to keep them on time or on frequency so you don't drift off frequency and interfere with somebody else. It's the same way with time. They all have relationships. So let's look at timing and synchronization and what we're going to go through. We're going to look at purpose of timing, timing standards, timing sources, time coordination and distribution agencies, timing jitter, and network synchronization. So first up is purpose of timing. The idea behind time is so we can get our equipment to talk to each other. Because if one isn't synced up correctly, then everything else is not going to work. Your phones that you have, your cell phones, all work off of the base of time. Whether it's a frequency time or TDM time. So you're going to be doing this throughout the rest of your life. You guys were pretty much, compared to when I grew up, you guys have got a lot more technology than I could ever fathom. Now, how many gamers do I have out here? Griffin, you a gamer?
I'd like to consider myself one, sir, yes.
Okay. Was that Javier? Did I say that right?
Javier, sir.
Okay, are you a gamer?
Yes, sir, 100%.
Okay. King?
Yes, sir.
Price?
No, sir.
Okay. Have you ever played a game?
Yes, sir.
Don't lie, Price.
She's played Far Cry.
Well, hey, I am not complaining about anybody playing different types of games. To each their own. So, Price, you've played a game. Okay, good. Was that Roundsley? Did I say that correct?
Yes, sir.
And you're a gamer, right?
Yes, sir.
And if I'm not mistaken, Airman Spore is a gamer, correct?
You know, sir.
All right. Stanek? I said that right?
Oh, yes, sir. I've been at it since I was 4 years old, sir.
Oh, Lord. Hall?
No, sir. I haven't played video games since high school.
But you've played a video game before, right?
Yes, sir.
Okay. Green?
Yes, sir.
All right. Alvarez? Senior Airman Alvarez, are you a gamer?
Yes, sir. I used to be.
Okay. As long as you are giving me some type of feedback. I'm going to try this. Rapoli? Did I say that correct?
Yes, sir. Well, I was playing Call of Duty till about 6 hours ago, so I'd say so.
And Sergeant Keenan?
Yes, sir.
Okay. Well, I want to say I didn't really like video games until about 2.5 years ago, and I play a massive amount of World of Tanks. So what do games have anything to do with timing? For those of you that has been in some really close games and all of a sudden your ping rate goes through the roof and you end up dying or whatever, that has everything to do with timing.
That's how controllers get broken and TVs, sir.
Yes, and I've seen a bunch of them on YouTube. It's like, why? I understand why, but why did you go off in a rage like that? That's money that you don't have, probably. So you are correct. Seen that on YouTube a lot. But those ping rates have everything to do with timing getting out of synchronization. So everything that we do in this particular course is going to be dealt with timing. So let's take a look at least what I have played with in my Air Force career. This multiplexer, I'm not sure if you can see my mouse, but this multiplexer, it's in the middle, is called an FCC 100. I've played with that many a time. I dealt with the signaling formats that we had to program in. So when you take a look at this multiplexer, you can see you have a NIPRNet. You have a lot of users on that one channel. Look at your local switchboard. You have a lot of users on that channel. Look at your SIPRNet. Again, you've got a lot of users, but it comes with a caveat. Look at the encryption. And then there's single users like computers or phones that have a direct link right into the multiplexer, and it's a single use channel. And when it comes out of the multiplexer, it deals with encryption, and then it's sent out the satellite antenna. This is what we're going to be doing over the next several days, is being able to put all this together with the multiplexer. You're going to see an NSM, and you're also going to see the equipment that it's got to tie into to get sent to the satellite. Everything in there is dealing with time. So we're going to look at time standards: apparent solar time, mean solar time, atomic time, universal time, and hammer time. No? You don't get it?
I got you.
Hey, gotta keep it jovial, right? So first up, we look at apparent time. This is the least accurate. It's basically sundial. You can look this up as far as the history of it. But when we get into mean solar time, this is where we started developing watches, and the biggest watch of all time that everybody knows right now is called Big Ben. It is under overhaul, I guess you could say. I suggest very highly you watch the History Channel on how it keeps time, because it references the universal time. Now, what started to develop here is these scientists were able to develop standards in where they could figure out, okay, this is the time we are at right now. And it started at Greenwich, England. So if you ever get a chance to visit London, if you happen to be overseas in the European area, please do so. They have a really good tour, so to speak, in there. We also reference this latitude line, the up and down line, zero meridian, I guess you could call it. This is considered the Greenwich Mean Time. And you're going to see that we interchange a lot of these acronyms for our time. You'll see UT is Universal Time equals GMT. You're also going to hear Zulu, UTC. All of these are interchangeable, but this is the basic part of how we get where time started. So how does it get its accuracy? Well, right now, our standard is atomic time. That's our reference that we have. We reference it to develop a standard. The standard is GMT right now. It is the world standard. We have something called the International Atomic Time, which governs what time it is in certain parts of the world. So when we look at UTC. Now you'll see that it says Coordinated Universal Time and then the acronym UTC. Okay, let me give you a little background on why that's different, because if you look at the acronym Coordinated Universal Time, it's CUT, not UTC. UTC is a French word for Universal Coordinated Time, or Time Coordinated, excuse me, French. So our analogy is, Coordinated Universal Time. Now, you can see that GMT is no longer the world standard. That's because in 1972, they decided to change it. It's still the same doggone line. The zero meridian is where everything begins. The idea behind it is we need that atomic time to make sure that everything is accurate, because it's it is the source where the time standard is developed. There are 24 different official time zones. The time zones depends on where you're at. Normally, what they did is they took the latitude and divided up into 24 sections, and that's how they got their time. But au contraire, I'm going to show you something really crazy here. So give me a second. You can see that dateandtime.com is where I'm going to go. So let me mute this and pull this one up. You see this date and time? This is the map from date and time, and you can, geez, I can't get my cursor on it. I forgot. This is a different widget that I'm using, and I gotta get used to it. This particular map, you can see that we have Eastern Time, we have Central Time, which is what we're in, we got Mountain Time, we have Pacific Time, we have Alaskan Time, and of course Hawaiian Time. Those are the 6 time zones that we have. There's also other territories that we have. But if you take a closer look at, let's say, I think it's India, you'll see that it has stripes in there, diagonal lines. That is because India decided that they were going to do theirs on half hours. But look at China. They cover 5 different time zones, but only have 1. Kind of crazy, ain't it? I didn't make this up. This is kind of, hey, this is impressive, really, because countries are what dictate what time everybody should be on. Now, if you go back to the United States, there are some states that do not observe daylight savings time. I think Arizona is one of them. There's certain cities that don't either, right? Yes, go ahead and speak up.
I was just saying, Arizona, yeah, that's where I'm at, and yeah, it really sucks when you go from being 2 hours behind someone to being 3 hours behind someone.
Yeah, they're looking at, to be quite honest with you, I am not a big fan of the daylight savings time anymore, because I don't see a reason why we should follow it. Most other people don't. I guess we just want to be different in the United States. Who knows? So I'm at anybody's liberty if someone can truly explain what's going on behind the scenes. But I've heard everybody wants to get rid of it. The excuse was back in the day we had the farmers, would get better capabilities of their time, and it's like, no, I farmed before because the sun comes up, you're out there, and it doesn't, you don't have an alarm clock. You have, when the sun comes up, you're outside starting the farming issues, and you don't come back in until the sun goes down. So during the summer, you got a long time of farming to do. During the winter, it's a shorter time. So I just do not understand that part yet. So there's your map. There's the dateandtime.com. It's in the URL. That's all you got to put in is date and time, or timeanddate.com, and it'll take you right to the website. One of the nice things about this website is I like to look up the eclipses that are in there. And I think we have one in June. I think it's a lunar eclipse that we have the very good chance of seeing. So there you go. You got some information that does not is not in your study guide workbook. So let's take a look back at our lovely slideshow here. You'll notice it says 0, time zone 0, 0 meridian, or Zulu. Always remember you're going to have local time in the shop and you're going to have Zulu time, because most of our missions are based off of Zulu time. Because if you had everybody trying to go by their local time, it would be crazy trying to figure out what's going on. So Zulu time is what we follow in the military. We have timing sources. This is what we use to develop timing standards. For example, I have 922 on my computer here. Someone else may have 921, 923, but if I tell you, hey, at 9:30, we're going to take a break. Well, it doesn't matter what timing devices you have. What just happened in this particular slide suggests that my computer just became the primary source. All of yours became a secondary source. Now, obviously, you want to make sure that your time that you're going to reference as a primary source is the most accurate. So, if you were in the classroom and I looked at the clock up on the wall and said, okay, we're going to take a half an hour break, be back at 9:30, that's your primary source. Your watch and everything else is your secondary sources. So that's where this primary source and secondary source come into play, because when you get into the more accurate systems, you always want to try to do your best to select the best and accurate time that you can find. There are two different types of oscillators that we deal with, quartz and atomic. Quartz is the least accurate. It uses something called the piezoelectric effect. So, Airman Green, do you have any idea what the piezoelectric effect is?
Yes, sir. 1 second. I believe it. I have notes on that. 1 second.
All right. Got to turn my volume up. I can barely hear him.
What was it? It was if you put an electric shock through an oscillator, it would vibrate, I think.
Yeah, exactly. So what you're doing is you're powering up that oscillator and vibrating that crystal or whatever it is in order to get a frequency out of it. And that frequency has two limiting factors. One is temperature and the other one is aging when it comes to its accuracy. Now, temperature, we can put it in what's called an oven and keep it at 1 temp, but the problem that you have is just like me, I age, so I can only do certain things. So after a while, I used to be able to play basketball. I can't play basketball no more. So obvious reasons, aging does have an effect on the crystals as well as you. And getting old stinks. There are two different types
Okay.
of... Go ahead.
I was agreeing with you.
Yeah. Oh, okay. Yeah. Getting old sucks. All right. So we go into atomic... let's try it again. Atomic oscillators. There are two different types, rubidium and cesium. They are definitely more accurate than quartz. So we just look at the atomic oscillators, in this case rubidium. I've dealt with the rubidium in the 206 palette. They're very accurate. They're also in the GPS, the older GPS satellites, and some of the ground stations. You can see how accurate they are when you compare it to a quartz, and this is rubidium, but the newest one that they have up in the GPS satellites are the cesium. It is more accurate than rubidium. And this is a comparison. You don't need to know how many cycles per second it is, but you just need to know that the cesium is more accurate than rubidium when it comes to atomic oscillators.
The 610th or the secret squirrel unit that we support and PML back at DM, they have a rubidium little time box.
Mm-hmm.
And every time it comes in, we gotta drop everything we're doing just to support those guys.
Yeah, because if you're off time with that bad boy,
Yep, and
your
it's got
encryption suffers.
as soon as they bring it to us, like it has to be plugged in and quote warming up for 24 hours before we can even touch it, so we can get back to its temperature and oscillation.
Wow. That could be the reason why they got rid of the 206 pilot in the Humvees. But I do know that you had a lot of frequency hopping that went on your Verk vehicle radios that they had, and the Army radios, and there's an HF radio in there also. So all of them dealt with time as far as encryption and time of day. So if your rubidium oscillator was off, yeah, you're going to have some problems trying to get time of day and sync up with your encryption and frequency hopping. That would make sense. So next up, we have something called time coordination. The idea behind them is they had to come up with, okay, how many seconds were in a day? And I just went to a website right before I got on. I went, holy crap, I didn't realize that they had a video that was this intense. It's kind of a rap style video, but it was really in depth. And I'll tell you about the website here in just a few minutes. Very good video. I was impressed by it. Didn't know that agency could do that. But anyway, the time coordination is developed so all the distribution agencies know how much is 1 second. One. So when we look at the distribution agencies, there's 3 that we reference. There's probably more out there, but these are the ones that we're most concerned about. We have BIPM, USNO, and then NIST. Now, BIPM is the international one. This one maintains everybody's clock throughout the world. So you have UTC is where that clock is at, and I will tell you the website is French, but it's all in English. Don't ask me why. And the URL is at the bottom if you want to go to it. But I'm going to show you what it looks like right here. So let me mute this and go to the BIPM website. That's the BIPM website. Kind of crazy. But you can see right at the top here, top left, you can see that the French words Bureau of International Precisions and Measurements. So that's the reason why they say BIPM. That's the keeper of time, as I like to say it. Maintains UTC. Next up is the DoD one, USNO. Now, the headquarters is in Maryland, but the actual timekeepers is right down the road a piece in Pensacola, where the Naval Air Station is. You can see this by just typing in USNO and you can get to the website, but there's a number right here, 202-762-1401. You can dial that up, and what you're going to hear when they pick up, it normally takes between 2 to 3 times before you can dial it and it will pick up, and it will give you a time hack. The first one will be Eastern time. The second one will be UTC time. Again, this is back at BIPM, and where they're seeing what the BIPM time is, or UTC time, Zulu time, at the 0 meridian. Next up we have NIST. This is the civilian side of keeping time. Now this has a lot of history, so if you go to the website, you will see the history. I think it says about us. I think that's what the area is, and you will see that it was developed somewhere in the 1940s, and it was based out of Maryland again. That's where the headquarters is, but they ended up having to take all of the radio stations, because this was time hacks over the radios, and put them out in Boulder, Colorado. That's the WWVB. And WWVH was put out in Hawaii in 1943. And again, these are all history-based items. And if you go to the frequencies of 2.5, 5, 10, 15, and 20, depending on the time of day, because it is HF frequencies, and this is megahertz. These are HF frequencies. You should be able to hear them. Most of the time, I can hear it either at the 5 or the 10 and 15, depending if we did it real early in the morning or in the afternoon. Then it's like the 10 and the 15. Every once in a while, we'll hear Hawaii alongside Boulder, Colorado. And you're going, well, what's the difference? Believe it or not, history dictates. The male voice that you hear coming out of Boulder, Colorado, again, has a history to it, but it's a female voice out of Hawaii. Again, history dictates. So you can see the area code and the number. Write it down if you want to impress your friends. It gives you just UTC time every 30 seconds. And if you looked on their website, you can actually see it drawn out. There's clicks, there's tones, and a couple other things that's associated with it. And it breaks out the 1 second in what is actually happening in there. And it's mainly used for not only for us, DOD, so when we are anywhere in the world, we can actually hear UTC time, but we can also listen in if you are a civilian and pull the timing that's off of those clicks and tones. And depending on what it is, we'll tell you which side of the half hour it's on. It's either on the from 12 to the 6 or the 6 to the 12, just by listening to the tones or clicks. Next up, we have something called timing jitter. You have short term and long term. What's it derived from? Normally that shift, and that's where your ping rate starts coming into play. Or if you like to watch a lot of YouTube videos and you get on one and it does a little circle, well, what's happening is your timing jitter is giving you grief. Now there's some ways to compensate for it. The short term uses something called elastic store. And that one I like to relate to YouTube videos. So when you go and click on a video, it's going to buffer first. You're going to have that pale line build up, and then you're going to have a solid line, which is the video and the audio is going to play, and hopefully it's in sync. You know, bye. No? You don't get it?
Yeah, I got it.
I caught you on that when everybody's going to sleep and bye. In sync. Oh, got it. Yeah. But anyway, just trying to keep you entertained at times. But this elastic store, that's that buffering that you get. And there will be times where you're going to catch up to that buffer, and that has everything to do with the timing jitter that's in place. The buffering is just, because the elastic store just cannot keep up with the way the video is played, because the data is not coming down the line quick enough. We also have something called long-term jitter. Now this one's based off of what they classify as unsynchronized clocks. In other words, you got one clock on one end and another clock on another, and the delay in time that it takes to go from point A to point B means that it will be unsynchronized by the time it gets there. The whole idea behind that one is we use something called phase lock loop to compensate for it. It doesn't correct it, it compensates for it to get everything back in time. We have 4 different network synchronization, 4 types of network synchronization. They're plesiochronous, I like to call it the dinosaur. You have mutual, master clock, and master slave. Now these are all terms that are still derived in the computer side. They haven't changed. So first up is Plesiochronous. This is I like to call it a little bit on the ad hoc. You guys have done ad hoc before, right? Where you can link one computer to the other and play your games. Well, the nice thing is it syncs up your clocks and you don't have to worry about it going from one side to the other. You do use what's called the elastic store with it. Next up, we have something called Mutual. This is where the clocks amongst each other are being synchronized with each other, but if you got one that fails, or let's just say you're an ad hoc with your LAN party or whatever, and someone says, I'm done, I got to go to sleep. So what they do is they can just shut down their computer, but everybody else is still in sync. Bye, bye, bye. Next up, we have something called a master clock. This goes back a long time ago when they had the English times with Big Ben. Big Ben was built to where they could hear time throughout the countryside, many, many, many miles. And they knew that this particular so-called master clock, because of the chimes on it, and they could hear it, they knew that, okay, this is a time we need to go to school. This is a time that we can break for lunch. This is a time, so forth and so on. That was the reason why Big Ben was built. And by the way, History Channel has a wonderful history. I think it's a 7 or 8 minute video on it too, in the way Big Ben was built and why. But there is a problem. Nowadays, it's not a problem because Big Ben is being overhauled. But back in the day, if Big Ben went down, everybody else's time was off. So until they got Big Ben back up, everybody was failing until Big Ben came back up. And that's the reason why we don't use it, is if the master clock fails, everybody fails. And I still remember this back in high school where we lost our master clock for changing of the classes, and they would have to get on the intercom and say, okay, you got 5 minutes, get to your next class, that type deal. That was the only way they could get around it. So we were on their time, not the master clock time. Next up, we have something called master slave. This goes back a while when we had hard drives and you would have to move jumpers. If you had more than one hard drive, one became the master, the other one became a slave. Now, with this master slave, this is what DoD uses, because if we ever get in a war, and since we're all based off of time, if we get one of our master clocks to go, another base is going to pick up. So that's the reason why I kind of like to say it works off of a pyramid, where you have the master clock or the master node at the very top, and you have 2 nodes below it. Then you got 3 nodes, 4 nodes, and so forth and so on. As the top node goes out, one of the other ones is going to slide up into its space, and it's going to be the master node. So you can see that it's a backup to the backup to the backup for what's called the master slave. At this point, we've covered all of purpose of timing, timing standards, timing sources, time coordination, distribution agencies, timing, jitter, and network synchronization. Any questions on time? Did I lose you?
No, sir, I'm here. I just didn't have any questions.
Okay. Sometimes feedback's a good thing.
Yeah, this the other 11 people in this class have a hard time with providing feedback, don't you guys?
Yes.
Exactly.
It's just, this whole thing is very, I don't know. If we were not on push to talk, it would just be a little easier for me to chime in, but it's just kind of weird pushing to talk for me, so I don't say a lot. Sorry.
It's okay, my young Padawan. You'll get it.
I did like your NSYNC references, though. I just didn't want to have to chime in or anything.
Also, Mr. Meyer.
Okay, let me turn you up because I could barely hear you. Okay, go ahead.
I found worksheets on the student files, so I got most of them except the TSM worksheet. It wouldn't work.
Okay. What I'm going to do is, if you can do what's called the @ and then put mayor and send me a message on what you're missing, I can go ahead and put it in the resource and make sure that it works before I put it in there. Would that work for you, sir?
Yes, sir.
All right. You're welcome. Anybody else having problems with worksheets and stuff like that? No? Okay.
I think it was just me. I lost mine. So.
That's okay. It happens in this wonderful world of technology. All right, so let me mute this and go to the next set of slides. So the next one we're looking at is 1 Bravo. And once we get done with 1 Bravo, we're going to break for lunch. This is where a lot of the students have problems with signaling format and PCM. So we're going to be looking at identify basic relationships of basic facts, state general principles associated with the principles, capabilities, and limitations of multiplexers. So what we're going to be doing for the next half an hour, 45 minutes is getting into what multiplexers are all about. Now, some of it I'm going to go through pretty quick, and that should be a sign to you going, okay, I just need to know a little bit about this part here, but I'm not going to tell you anything else. So we have, everybody knows that we're going to do 70% on the test here. That's the minimum that you can get to go on to the next block. Now, you can only miss 12 questions out of 40. So in other words, you got to get 28 of these correct. There are 2 tech orders that you will have access to. There's electronic C's and D's and paper C's and D's in the testing lab. So if there's any part that you're in taking the test and you're having a question about the question, raise your hand and I'm going to give you a little advice on that. Sometimes by asking, can you please reword that? An instructor can go, oh, this is what it's asking for. At least that's what I try to provide you with. Or if they're smart, they will say, well, you remember when Mr. Mayor was talking about this part and he said this, this, and this. It's an idea to get you, trying to regurgitate that information that I gave you earlier. So hopefully they know what to do when you raise that hand and ask that question on the question. They're not going to give you any answers, and they're not going to, guide you through it. They may even go, well, you need to look in the TO, maybe this page or this area. So those are some hints, because I've seen students where they'll get on a TO question and not use a TO and try to pull it out of their memory. Most of the time that doesn't work. Please use the tech order or the C's and D's. So enough on the test. You've had my little say on it. All right, so we've got the AFSC application. You're going to maintain multiplexers. In fact, you're going to see the NSM. You're going to see a bunch more multiplexers out in the field, depending on where you go. You're also going to play with one in Block 9. Fun stuff. We're going to look at general multiplexing terms, input data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, analog to digital conversion. Here's your terms. The difference between analog and digital. If you know what analog is, digital is the opposite. So if you look at the word infinite number, digital is going to be a finite number. Unlimited number is analog. Digital is the opposite, which would be limited. And then I like to throw in a word called indiscrete, meaning it's all over the place, and digital is discrete. Those are three terms that if you know the set of one, you should be able to identify the other. Next up, we have bit. This is your binary digit, not to be confused with byte. Bit are ones and zeros. Multiplexing. This is where you're going to take users or channels, and it should be more. It should be two or more channels in parentheses users, because users can be a single entity, just one user for one channel, but you could have multiple users on one channel. Like I showed you back at the FCC 100 where you saw a SIPRnet that had many users on it, and that was on one channel. You also saw where one computer was using one channel. So channels are a better way of saying that. Now what does it do? It takes the multiples of all these channels, combines it into one signal and sends it out. And then at the same time you're also getting another signal coming back in, and you're being able to split it apart and send it to the channels or users. It can be analog, it could be digital, voice, video, or data. So this gives you an idea on how we look at multiplexers. You have channel 1, channel 2, channel 3. Channel 1's diagonal lines, channel 2 is a solid, channel 3 is a horizontal. You can see right here at the first part here, as they go down, the multiplexer is taking information from every one of those channels in a certain time period. Sampling. This is how we're going to look at, not going to the buffet now, guys, and getting all your different types of food and trying to figure out which one you like the best. Sampling in our case is we're going to take an analog signal. We are going to take an individual portion of that signal and measure it, and every one of them is going to be, like we have 1 second, we're going to have sections in that 1 second. Every one of those spaces in there is going to be equal, where we sample where that analog signal is in that time. And it says, like I said, sequentially, it doesn't make any sense to try to measure number 1 and number 6 and then number 4. No, it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Next up is frame. This is probably a new term for you. This one says it consists of a sample from each channel. In other words, if you look at frame 1, it took a sample from channels 1, 2, and 3 and put it in what's called a frame. Again, sequentially. It doesn't go 1, 3, 2. It goes 1, 2, and 3. Non-information. Go ahead.
Is each frame built up of one sample, and then when it's sent out, it's turned back into the actual signals?
Well, the idea behind a frame is when it gets to the distant end, the multiplexer is going to know, okay, he just sent me this frame, and I know now where channel 1 is, channel 2 is, channel 3, and so forth and so on, so I can put the appropriate data in each one of those channels. If you didn't have a frame, it would be all over the place.
So the frame is kind of like the sync then?
Yes.
Oh.
And there's more to it, but I hesitate to get in depth on it. I'm just trying to give you the information that it's very basic.
So pass the test.
Yeah, to a certain extent, because we can go in and start Googling this stuff and really get deep. I don't like going down a rabbit hole unless someone really is genuinely interested, and I think it might help them out to understand what we're looking for. So I like to touch upon it, and if you're still having confusion, I'll go just a little bit deeper to get you to, here it comes, understand it. I'd rather you understand it and pass the test understanding than just memorizing it and flushing it, and you need it when you get out in the field. That's the bad part. Non-information bits. This bottom line, frame bit. Well, gee, that's how we sync up everything. Stop and start bit. Okay, and then stuffing bit. What does it mean by non-information bits? You have, in our case, we're going to be talking a lot about an 8-bit word. An 8-bit word means it is considered the intelligence that the computer needs to decipher. The non-information bits are not part of that 8-bit word, but tell the computer, hey, this is channel 1. This is where the 8-bit word starts. This is where it stops. Oh, and if I'm in isochronous, then I need to stuff it with irrelevant data just to keep it on time. And we'll go there in just a few. Next up, we have bandwidth. Now, this can be looked at the speed or what the frequency range is. Those are a couple different ways to look at bandwidth. Figure out what it's asking and then go with that part. Next up, we have async. Yeah, the problem with async, you got a lot more data that goes along with it. We call it overhead. Overhead is the non-information bits, and there's more to non-information bits than what we have just gone over. I'm hesitant in pulling up Google just to look at. I would say in an 8-bit word in an async scenario, we are looking at an extra 5 or 6 bits, depending on what style it's in. So we're just going over the basic stuff, which is stop and start bits, framing bits, and stuffing bits. Async is going to use definitely the stop and start bits, because what it likes to do is it likes to conserve its bandwidth if you're not using it. By the way, your computers use async. Then we have synchronous. This one is where we see items like if you were doing, and this comes to mind, if you had cameras on your house and you needed to view them all the time, like security does in the casinos and that, you would literally have to use synchronous because you want to keep those cameras on all the time. So you're looking at that video. That is one of the major uses that I can see where synchronous comes in. You're not wasting the data. You're seeing the data propagate on the screen, especially if you got a 16 camera system like I do. I'm using 16 cameras. I can go up to 32, but I don't need 32. But 16 cameras does my house pretty doggone good, and I can cover and overlap on them. Now, with these cameras, I can view them all at once. And that's what I want to do. I want to see what's going on. That's what synchronous does. It provides me data continuously, and there's nothing missing. Okay, if you had a 16-channel multiplexer and all of them are synchronous, I'm going to have 16 cameras. There you go. I'm not missing a beat. If I had async, that's a lot of bandwidth when you compare it to synchronous. And we'll go over that in just a minute. Isochronous. This one is a beast. What does it mean by it's a beast? If you take a look at underneath the isochronous, asynchronous at a synchronous rate. So in other words, you got stop and start bits along with your framing bits. And if you don't have anything to put in that channel, you got to stuff it. So if you had an 8-bit word and you didn't have any information to put in there, you're going to have to stuff it with 8 bits of zeros, in my opinion. Now, you look at isochronous, and again, this is back in the olden days where you had, and vids is what comes to mind on that one. You would have the cameras, but you would also have the sensors coming in at the same time. So that's basically an audio and video that's coming in, but it's continuous, and you're not wasting any bandwidth. But if you had to do, let's just say, our computers doing that. And we didn't, let's say we went home at 4 o'clock. Well, now we're wasting all that bandwidth and using what's called stuffing bits. So it's wasted bandwidth. Now, when we dealt with isochronous in the FCC 100, they classified it as a lot of overhead. And what does it mean by overhead? That's the extra information that needs to go on to keep things in synchronization from one end to the other. It's a lot of bandwidth. Again, VIDS is the one that I can think of using isochronous. I don't see it being used out in the field very much anymore because everything is going to most everything is going to async. We still have things that do synchronous transmissions. FDM, that's the frequency division multiplexing. This is what I classify as the first use of cell phone technology. And I still remember the day where they had, I think it was called StarTex. It was a flip phone. Woohoo! Everybody was happy about it. Yeah, you still called, but you didn't have texting, you didn't have the apps or anything like that. But the problem with FDM is you're using a frequency to put all of your information on, and you're going to send it to the cell site. The cell site's going to decipher it and send it on. But the problem is when you went from one cell site to the other, you'll notice that modulator or user A's on 82.0 and 83 gigahertz. Well, the problem with that is when you went from one cell site to the other, and the other cell site was maxed out, in other words, there were no more frequencies for you to use, you got dropped. So that's the fallback of FDM.
Can you hear me now?
Yeah, I can hear you. What happened? You dropped off?
No, it was a bad joke for the Verizon guy.
Oh, who's the Verizon guy?
He says, "Can you hear me now?" in the commercial.
Oh yeah, that's right. Now he's with, no, that
Sprint.
was, yeah, okay, Sprint. Trying to one-up Verizon, I guess. There's a YouTube video on it, too, a spoof, where he's going around, can you hear me now? Can you hear me now? And this goes on for like 2 or 3 minutes, and then finally the guy just gets fed up, and it's hilarious. Check it out. It's on YouTube. I'll leave that one alone. So TDM, time division multiplexing, is what's happening now. You get one frequency and you can go from cell site to cell site, and it shouldn't drop you off now. And by the way, it's called FDMA and TDMA for your cell phones and the way they're used now. And we can get into more deeper. So TDM, you can see that we have frame 1, 1, 2, 3, 4, the users, and so forth and so on. Not spending a whole lot of time. You just need to know the types of multiplexing on that. So you have synchronous and asynchronous. Synchronous is assigned time slots to all channels, whether active or inactive. That's, it's like the train pulls up. It's got 12 boxes. If you don't have X amount of customers going in one of the boxes, then, hey, oh well. It's going to close and then go on. You are going to waste bandwidth that way. Whereas async, well, let's go through sync first. You can see that in frame 1, all of our users are filling up all the train boxes here. And then when the next train comes in, you'll notice that Charlie, number 3, there's nothing in here. So with synchronous, you're going to have to make sure that you still open it, still close it. Oh well, nothing in there. It's wasted bandwidth. And of course, you have frame 3 and frame 4. You can see frame 4 only has one of the 4 users in it. Then we have async. This one depends on, for example, the students that are in the dorms. You're trying to get online when everybody else is trying to get online. You have to wait your turn. is what it amounts to. If it was like dark 30 in the morning, you probably could get online without too much of an issue. Why? No one else is. That's the disadvantage and the advantage of having async. So depending on the time of day and how many users are on that time of day depends on how long you're either waiting, or you can have the whole bandwidth to yourself. So it's going to speed it up, and if you're playing a game at, let's say, at 2:30, 3 o'clock in the morning, it's going to be pretty quick. Unless you're playing the European server or the Russian server, like I've done once in a while. It's even worse when you go down to the South American server. They have a lot of bots down there. There's only like 2,000 or 3,000 that play online there, as opposed to North American, which is about 25,000 at any given moment. Fun stuff for World of Tanks. I'm not plugging it. I'm just telling you what's happening. Asynchronous, you can see with each of the frames that frame 1 has all 4 of them, frame 2 has 3, frame 3 has 2, and then frame 4 has 1. So as it gets toward the end here, it's going to become quicker and go back to frame 1 to see if there's anybody else that's going to be on it. Asynchronous data. This is what it looks like. You have your framing bit, you have a stop-start bit, you have your 8 bits of data in there. That's your intelligence. So your start and stop, your framing bit are all non-information bits, even though that they're meant to tell you where everything is going to go. Asynchronous at a synchronous rate, better known as isochronous. This is where on frame 2, where you're missing Charlie, you're going to have to put 8 bits of non-information in there to keep it on time. That's the disadvantage of isochronous. And by the way, if you guys have ever watched Tron Legacy, what was Cora? The character Cora. What was Cora?
She's an ISO.
She's an ISO. Yeah. Oh, gee. That's what we're talking about. If you hadn't noticed the background on how the ISOs got developed, there you go. Watch it in depth this weekend when you get to that point of how they explain how they're going from their, the gains and programs and so forth and so on when they make isochronous. All right.
It's on Disney Plus.
I'm sorry?
It's on Disney Plus.
Oh yeah, streaming. That's a good movie. I liked it. All right, deep multiplexing. If you multiplex it in a certain, like ISO or synchronous or asynchronous, your demultiplex has to do the same thing. And hopefully all the information and non-information bits that came along with it will be able to separate it out and be on time at the same scenario to where the distant end can decipher what's going on. Because nothing is worse to have your vids showing what's happening out there. You got your sensors and that. Your sensors all of a sudden go off, and back at the other place where you're viewing it, nothing happens. And that's a bad thing. That means your demultiplexing is not happening correctly. Next up is signaling formats. I have 10 o'clock or 10:05. Let's take 10, be back at 10:15 because signaling formats is where it starts getting kind of crazy. All right? So we're going to stop here.
Yes, sir.
And be video I did, huh?
Yes, sir.
All right. Is everybody back and ready to go? No? Hurry up, right? So let me go down the list here. Griffin,
Here, sir.
Javier,
Here, sir.
King. I saw you click it, but nothing.
Can you hear me now?
Yep. Verizon. Price?
Here, sir.
Roundsley?
Yes, sir.
Okay, I heard Spore. Stanek?
Yes, sir.
Hall? Green?
Here, sir.
Alvarez?
Yes, sir.
Rapoli?
Here.
And Kennan.
Yes, sir.
Rapoli, there's a background in your name. I had a supervisor called Rispoli, Rispoli. When I first saw your name, I went, no, it's Rispoli, not Ripoli. Good supervisor. So your name is a good thing.
Well, that's good.
Yeah.
I wouldn't tell him that. He doesn't need to get his head bigger than it already is.
Trying to build them up, okay? All right, so we're going to look at signaling formats. Now, signaling formats is what most of our multiplexers are going to do. You're going to see this in the NSM tech manual, and hopefully we'll be able to go over it by the end of the day. Excuse me. We're going to look at non-return to zero, return to zero, and CDI, conditioned diphase. So let's take a look at each one of them. I always like asking this question, so Airman Spore, do not say a word. So this is a question. I'll go down through the list here and ask you, do you read it left to right or right to left? Griffin, what do you say?
I mean, I generally read left to right, but when I look at a number, I don't necessarily think about it. I just kind of see it and then interpret it.
Okay. Javier?
I read it left, right.
Okay. King?
Left or right?
Price?
Left or right?
Roundsley?
Right to left.
Woo, different.
Go.
Stanek? Don't change your answer now.
Oh, well, I mean, on bigger numbers like this, typically I'll read left to right. But sometimes it depends just on the number, because, like, you want to see how many zeros there are, right? So you kind of analyze that first and then start reading left to right from kind of analyzing it right to left, I guess.
Okay. Hall? Okay, it clicked, but it didn't come out with anything. Okay, you can put it in chat. Green?
Left, right, sir.
Left, right, and then Alvarez.
Right to left.
Right to left, another different person. Rapoli?
Right to left.
Right to left. And Kennan's already spoke what he thinks it is.
Well, I don't really go right to left. I look at zeros.
Yeah. Well, you should always start from right and go to left, because that's where numbers are made. You don't know what that one is. You got to start all the way from the right-hand side and go to the left. Most people always say what you guys have been saying all along, that, hey, I'm going to read that number from left to right, because when you read a sentence, it's always from left to right. Well, numbers, signals, and everything else is always from right to left. Now, you're going to see in this particular course, most of the items should be drawn from right to left. There is one or two things or one or two signals that are in the slides that are drawn incorrectly and are drawn from left to right. And they shouldn't be, unless they're in particular scenario here. So as you can see, we always start from right to left because we got to identify the ones, tens, hundreds, and that's where those zeros comes into play, so I can understand what you're looking at, especially a number this big. With 8-bit words, we always start from right to left, and I've drawn down here on the bottom how the 8-bit word is put into place. So we have the 1s, the 2s, the 4s, the 8, the 16, 32, 64, and 128. And the reason why I put that in place is when we get the PCM, you start to understand, oh, this is how it works. So those are 8 bits, 1 through 8, and we have something called a clock cycle. A clock cycle being from right to left. Each cycle always starts at the 0 and goes to the positive. It's always assumed that when a signal starts out, it should go from the 0 line to the positive line first. Unless it's a signaling format, then it's going to be completely different. But our clock cycles, how we are able to place the data in there to keep it on time or in sync. Bye. Now you want to go look that song up and listen to it. So the first signaling format we go to is NRZ, the name, non-return to 0. And what does it mean? We're looking at the clock cycle. We have where it goes up for a small duration and then goes back down to 0. That's our clock cycle. Well, in that clock cycle, we got to pass data in there to make it do what we want it to do with NRZ. Now there's two different types of NRZ. You got neutral and polar. Now the one thing about NRZ is this sentence right here. Most common data format within a multiplexer. I do not know of any multiplexers that I have come in contact with that had anything else other than NRZ. It will take the incoming data, let's just say that we've got users or channels out there, and they have different signaling formats. So when it comes into the multiplexer, it's all going to change to NRZ. So whatever the signaling format is that computer, the video, the audio, whatever it is, it's going to change it into NRZ. It's going to take it, put it in an aggregate, and send it out. Now, whatever it sends it out as, most of the multiplexers I've dealt with, there's two common formats that I have seen, which are CDI and NRZ. But again, it's changing it from NRZ to a CDI. So internally within a multiplexer is NRZ. We're going to look at neutral and polar. The first one is neutral. It has a 5-volt difference with our data. You'll notice this last portion right here, it is not self-clocking. In other words, when we formulate our signaling format with our data to resemble our data, we also have to send a clock cycle with it. So let's take a look. Here is our clock. Here is the data that we're going to do, and this is the signaling format that it's going to represent. You'll notice that the clock cycle goes up and then back down. In our case, most clock cycles I have seen out there is always from 0 to 5 volts. In this case with NRZ, we do have a 5-volt difference from 0 to 5. But on that first clock cycle, the word non-return to 0, we always begin with a 0 if the data is 0. So we are making this signaling format to represent the data with the clock cycle. The next clock cycle comes in, our data is a 1. In our case, logic 1s always go up. Halfway through the clock cycle, it doesn't return to 0, hence the name non-return to 0. We have another data of 1, and it stays at the +5. Then we have 3 zeros in a row, and it stays 0. And as you can see, anything that changes as far as the data is concerned, it will change to that. This is the reason why this signaling format does not represent anything like the clock up here. So we got to send our data, which is our signaling format that represents the data, and we also have to send a clock down the line.
So is that the main deal behind it? Not return to zero just because it doesn't have a clock to keep it at zero?
Yes. The clock cycle is what keeps everything in time, and if your data doesn't represent what the clock cycle wants to be doing, then you need to send the synchronization with that clock along with your data. So all the data, yeah, go ahead.
That's what makes it not return to zero?
Correct.
Okay.
Is your signaling format. So the next one we're going to look at is something called polar. Neutral and polar, what are the differences? 5 volts versus 10 volts. Now you'll see this line says a 10 volt potential over longer cables. Well, when you send digital down the line, you are going to encounter resistance. And when you encounter resistance, especially if it goes from 0 to 5 volts and back down and so forth and so on, as you get further out, that 0 to 5 volt difference may be 3 volts or 2 volts. Well, when it gets to the distant end, it doesn't know if it's a 1 or a 0. So that's the reason why you got to go with a polar, which gives us a 10 volt difference. Now, this time we're going between a positive 5 and a negative 5, which gives us a 10 volt difference. But I can go down further on a cable with it. I can see that when it gets where a neutral started, where it could not differentiate whether a 1 or 0, the 10 volt potential, you'll be able to see that. There is a difference between a negative 3 and a positive 3. Well, yeah, that's a lot more different than only seeing a 2 volt difference. You'll see the bottom sentence, it says not self-clocking.
Is that just due to signal loss or power loss across the cable?
That is true. You can go further with a polar signal, but you still have to send a clock with it. So not only are you sending the data of the signal with it, but you're also sending the clock cycle to tell the distant end, hey, this is how my data runs as far as synchronization is considered. So all this happens is if you take a look at this signal, we just made it bigger when we're doing the polar. That's the only difference. We have a 5 volt difference versus a 10 volt difference. Longer data or longer cable lengths is what we can use. Still need to send a clock cycle to the distant end. So non-return to zero, whether it's neutral or polar, you have to send a clock cycle. In other words, it is not self-clocking. So let's take a look at the next signaling format, which is RZ, return to zero. So wherever that data is, it's got to go back to zero halfway through the clock cycle. There are 4 types. We got neutral, polar, bipolar, and bipolar with zero suppression. Let's take a look at each one of these. Neutral, same thing with our NRZ. It still can't go further down the line, even though it's a different signaling format. The only difference is when you get halfway through the clock cycle with a data of 1, it's going to go back to 0. The namesake, return to 0. So we still have to send a clock cycle with it because it is not self-clocking. But you can see that halfway through the clock cycle, it does kind of resemble that clock. Now, again, it is not self-clocking. It isn't until you get to polar that you will start to see self-clocking. Now, this one's going to be pretty easy to identify why it is self-clocking. Now, 1s are a +5, 0s are a -5. Now, these are the logic zeros, not to be confused with 0 in voltage. So let's take a look. You can see halfway through the clock cycle, and this is a data of 0, we're going to go down to a -5, and then come up halfway through the clock cycle. So right away, we can already see that this is a representation of the clock here. The next piece of data, which is a 1, we're going to go to the +5 and then back down. Again, another representation of the clock. It doesn't matter if it's a -5 or a +5, but you can see halfway through the clock cycle, we're doing something. So this whole signal, RZ polar, is self-clocking.
So when our clock is at 0, our signal is at 0 volts.
Correct. Big time. Depending on what our data is, will determine which way it's going to flip. So every clock cycle, it is doing something halfway through the clock cycle. So at the dissonant, it already knows that, hey, this is self-clocking, and I can get in sync with it. That's the advantage of not having to send a clock. So now you don't have to send extra data with it. So RZ polar is self-clocking. We have something called RZ bipolar. Now you'll see that, again, logic 1s alternate between the +5 and a -5, and logic 0s are always represented by 0. So this is kind of represented to or RZ neutral in a way. You're going to see the difference is when we see another data of 1, it's going to do something called alternate with bipolar. See the difference? So if we were at RZ neutral and had these two data pieces of 1, this piece would still be in the up position of the +5. But because it's called alternate mark inversion, heed those words, because you're going to see them in the afternoon, it's going to flip-flop. That's that alternate mark inversion. For every data of 1, it's going to flip-flop, whether it's in the -5 or the +5 volts. So you can see the first data, we're always going to go to the +5 because that's the way we like to draw things. And then when we see the 1, the next one, we're going to flip-flop, and so forth and so on. Again, you need to send a clock cycle with it. When you get to 0 suppression, it becomes self-clocking. So now we have two, count them, two different types of self-clocking. One is RZ polar and RZ bipolar with 0 suppression. So those are two different self-clocking modes. In other words, I don't have to send a clock with it. Now, we have something called a bit violation. This 0 suppression determines where the bit violation happens. It's a little difficult to understand, but just keep in mind the zeros. There has to be a certain amount of zeros in a row before it flips into the violation mode. So we're going to look at our bipolar with 0 suppression. In this case, we're saying that on the 4th 0, we're going to throw a bit violation if we have 4 zeros in a row. You can see we start off with a 0 and 2 1s. So we flip-flop. We see we have 4 zeros in a row, and because we've told the dissonant, hey, if you see a bit violation on the 4th 0, we're going to see this violation. Now, what exactly is a violation? What it does is that when we see 4 zeros in a row, it looks back down the line here and says, well, gee, I'm supposed to go to the +5 for the next data of 1. In this case, I've had 4 zeros in a row, and I don't like it, so I'm going to do what's called a bit violation. I'm going to emulate whatever it was the last data of 1 to tell the computer on the dissonant, hey, I got a bit violation, so get back into sync. Bye, bye, bye. So if this one was a +1 or a +5, this bit violation would also be a +5. So it looks back down the line as the last piece of data of 1 to throw that bit violation. That's how it sees on the distant end that there is a problem.
Is the bit violation, or the number of bits, is that set by the user?
It's set by what you program in. So theoretically, you can change that. Because
So
when
it
you,
doesn't have to be before?
it doesn't have to be 4. In fact, let me give you an idea here. Depending on what type of lines you have, for example, I've got one where it says Bravo 8 Zulu Sierra, which is a North American term, and I looked that up, and it says for every 8 zeros, if the 9th 0 is, if the next piece of data that comes in is a 0, I'm going to throw a bit violation on it. They've got one which is called Hotel Delta Bravo 3, which is Europe and Japan. This one is telling you on the 3rd 0, you throw the bit violation. So depending on how you program it in will determine where the 0 is thrown. You don't need to know that. I'm just giving you some information that I've researched. You just need to know that if we have 0 suppression, there will be a bit violation determining on what you've programmed in there. Now you can program the NSM accordingly. You can put in, bipolar with 0 suppression. I think I'd have to look at it, but I think it's a T1, E1 lines where you can do that on. Again, it's a program, the GUI, that you're going to use when you get to the NSM lab on Monday. You don't need to know what 0 it's being thrown in, but you need to know that we have something that is self-clocking called bipolar with 0 suppression. We do have bipolar. And by the way, anything that you see with says RZ bipolar, they will also classify it as alternate mark inversion, Alpha Mike India. And you'll see that in a tech order or tech manual this afternoon. I'll point that out to you.
And when you have the bipolar, you'll never have 2 logic signals going in, quote, the same direction. One will be positive and one will be negative.
That is correct when you have pieces of, when there is no bit violation and there's data and you have the 1s, they will alternate. But the only time they won't alternate is when you have a succession of 0s and you need to get everything back into sync.
Right. And that's the same with just RZ bipolar without 0 suppression too, right?
RZ bipolar will always be flip-flopping. There is no violation on that, and you have to send a clock cycle with it, or a clock pulse or whatever. All right, so everybody got the bipolar with 0 suppression and down, I hope. It'll become clear when you start seeing the NSM. And we go through this because most of the data formats that you will see that we're going over is in the NSM. So now let's take a look at CDI. If you research this on Google, you will not find anything on CDI. You'll find something on a Manchester diphase. This is where everything started. It is my suspicion that we call it conditioned diphase, CDI. I don't know why I can't find anything on it. I'm still looking. I'm not a big-time researcher. I just kind of casually look. So it's probably out there. I just haven't come across it yet. And I've been looking for 2 years. CDI. The big thing about CDI is one word. Transitions. Yes, it still uses the 0 to 5, but it deals with something called transitions. Logic 1s only have 1 transition within the clock cycle. There are 2 transitions when we deal with logic 0s. Oh look, CDI is self-clocking. So now we have 3 self-clocking modes. Roundsley, can you identify the first one? Roundsley? Airman Roundsley? You there? Uh-oh. Roundsley. Interesting. Hall, can you tell me? At least one self-clocking signaling format that we've gone over?
NRZ bipolar?
Spore? Is he correct?
I'm pretty sure, sir.
You broke up right at the front. Is he correct, Airman Spore?
Yes, sir.
So what did he say? See if I'm hearing the same thing you guys are hearing.
RZ bipolar, or RZ polar, sorry.
RZ Polar? Yes. So, Aaron Price, what's the second one that we talked about that was self-clocking?
RZ bipolar with zero suppression.
Yes, ma'am. King, what's the last one that is self-clocking?
CDI.
CDI, okay. Just making sure you're all there. Roundsley, are you still with us? Anybody have an idea where Roundsley is? I wonder if he vacated the premises here and
I think his internet might be crapping out, sir. I don't really know what else it could be.
Okay. Yeah.
I was going to say that maybe he just went to the restroom. I know I did that earlier, but I brought my phone, but maybe he didn't.
Interesting.
Also, sir, I haven't taken this block yet.
Who is it that has?
Nobody. I sent you a message about that.
Huh. Man, on the thing it says 11 personnel, and I got 12.
I did retake block 5, though, so I am a washback, but I didn't wash back from this.
Okay. I apologize. This doesn't make any sense. I have 11 on my sheet, but yet there's 12 in the class.
Yeah, last block was like that too.
Huh.
It's like he came into us in block 5 to take the test, and he's with us. He's part of the team now. He's just not on the roster apparently.
Okay.
What he's saying is I'm not part of the team.
Oh, you're part. New guy.
New guy. Yeah, he's new for a while, so Airman Spore needs to be added. And that's A1C. Make sure I get it correct.
Rousey didn't have a fire alarm or something. Like, doesn't he live in a different building than you guys?
No, he's in my building and there's no fire alarm.
Okay.
Well, I see him on the right-hand side, but his avatar is showing idle. Stanek has a do not disturb on his, as well as Griffin. Everybody else is in green.
Pinged with things, sir. I really, after using this platform for like 3 years, it's gotten really annoying every time I hear a button. So I just turn on do not disturb, and it's a kind of a band-aid fix for it.
Yeah, I keep mine on Do Not Disturb and then keep Discord open. And so if I see on my application on the bottom there's like a red dot, then I know I have a notification to respond to.
Roger that. Okay. All right. we'll fix it. Remember, this is a platform that we just started using back in April. So a lot of this is relatively new to the instructors as well as the students is using this in this type of format. I'm used to playing tanks, playing with my platoon buddies, shouting raging thoughts and having puns go crazy. Alright, so yes, the 3 self-clocking modes, RZ polar, RZ bipolar zero suppression, and CDI. CDI is a lot different because it uses transitions. Everybody else uses the voltage. So here is the transition waveform that we have, that you can see we have a data of 1, and you can see they have 2 transitions in it. We have a data of 0, I apologize. We have a data of 1, there's only 1 transition. You can follow this through. Every time that there's a 0, you have 2 transitions. Anytime that there's a 1 transition. Now, when you get over here, and this is where things change, with the 1 and then back down with the 2, then you have the 1, and then this one with the 2 transitions goes down to the 0 and then back up to a high. So that, even though it has 2 different transitions, it doesn't care if it's a 5 volt or a 0 volt and where it lands at. I will tell you there is one difference about CDI besides the transitions. In CDI itself, there are times where the transitions are not in sync with the clock cycle. Don't ask me why that happens that way, but the distant end can still sync it up using phase locked loop. That's the only thing that I can get out of it. Do you need to know that? No. You just need to know there's 2 transitions for a 0 and 1 transition for 1. Transitions is the key. So now we go into something called Nyquist theorem. And hopefully we'll get through this before lunch. Nyquist theorem, Dr. Nyquist said that we're going to take 2 times the highest audio and sample it times that. So in our case, most of our radios start around the 300 to 3K. There's some that go to 3200 or 34. I've seen one as high as 36. Do you really need to be that high? Not for voice communication. You're not going to be singing in the middle of a battle. It just ain't going to happen. But there will be a lot of squeaky voices and a lot of deep vibrato voices. And what they tried to do is keep the sampling rate within a certain area. So what he said is, all right, just to be on the safe side, we're going to keep this at 4K, and we're going to sample it 2 times that 4K to give us 8,000 samples per second. Now, why does that have an important analogy for us? Well, we deal with something called PCM. You guys have done this in Block 2. You came across it. You had the handset that went into the radio, and it changed your analog voice into digital, didn't it? Oh, yeah, it did. And then, of course, it put it on an analog waveform to be sent out, so your digital information is actually modulated on an analog waveform. You'll get to see this when we get into modems too, by the way. PCM, pulse coded modulation. Before I go any further, has anybody ever heard of the free software audio program called Audacity?
I've heard of it.
Okay.
I use it, sir.
Good.
I've heard of it.
Yeah. Well, I use that when I'm
I think
trying.
I heard it was Napster. So.
That's old school for us.
Exactly.
That's downloading music. This one is the expanded version of PCM, because it is PCM when you're saving it to the MP3. When you are sampling, and you could probably relate to this, Tech Sergeant Kennan, is when we first got CD players, they came with a sample rate which was 8,000 times a second. We thought we had it made. Woohoo! I love our audio gear. And then it went from 8K to 16K, and then to 32, then to 64, and we couldn't keep up. Nowadays, if you went to Audacity, they have 3 modes. The last mode's called Insane at 320K of sampling. That is ridiculous. But with PCM, we're only dealing with voice. We're not dealing with music. So let's take a look at each one of these 3 steps to convert analog to digital using pulse-coded modulation. First step, sampling. What we're going to do is we're going to take the audio signal. We're going to divide it into 8,000 sections. Each one of them is going to be equal. And then we're going to use the pulse method. In other words, we're going to measure up to the pulse and figure out where that line is on the voltage. And what we're going to do with that line is, by taking that sample, we're going to put it onto something called a quantization table. Now, most of you have probably dealt with a paper or a graph paper of some sort, and you'll notice that each one of the boxes are equal in width versus height. And what they've done here is we're going to put each one of those samples on a horizontal line, and each one of those width boxes is how far apart they're going to be. Now, we have something called a quantization table, and that's what that graph paper is going to represent. And that's just to give you guys an idea of what's going on. This table goes from a 0 to positive 127, and from a 0 to negative 127. Now, for most of you, you're going, okay, I don't get it. But I want you to go back to that 8-bit word. 8-bit word. When you go 1, 2, 4, 8, 16, 32, 64, and you add all of those, you come up with, wait for it, wait for it, wait for it, you get 127. Interesting. On the quantization, when we apply these little voltages to this table, we have 127 steps on the plus side and 127 steps on the negative side. We have 2 different types of table. One's a uniform, one's a non-uniform. The problem with uniform quantizing is when it falls between a line, we have to do something called rounding up or rounding down. These are considered quantization errors. On a uniform table, they are a problem because you're going to have a lot of rounding to do. These errors, if there is a lot of them, will sound a little bit like distortion. At least that's the way they classify it when you Google that. When you get into non-uniform quantizing, what they've done is they said, you know, most of our voices is between this level and this level. And what we're going to do is we're going to cram as many lines as we can so we don't have as many quantization errors. So we still have 127 steps. The difference is as they're closer to 0, those steps are smaller, so where each one of these sampling items can fit on a line instead of having to round them over and create quantization errors. So with that in mind, you still have errors, especially if you got somebody that's got a really high voice or a really low voice, and you just can't get away from it. But by squashing those lines together, you can at least eliminate a lot of the quantization errors. The next part is called encoding. So you have sampling, quantizing, and now encoding. There are 8 bits. Wait a minute, I just told you there was 7 on the negative and the positive 127. Interesting. Oh look, the first 7 bits gives us the 127. The 8th bit is going to identify whether it's on the positive side or the negative side. Oh look, we have an 8-bit word. Amazing. Now, so let's take a look at this chart here. You can see that we've got some figures in here, and you see the first one we're going to come across is a positive 2. That's this little device right here. Notice that we're going from left to right. Bad on them. So when we draw an 8-bit word, which they got correct, they just didn't do the signal right. You go, here's your 1, here's your 2. So that is a +2. All your zeros are considered positive numbers. When you get, let's just say, a -5, well, there's a 1 in the 1 place. There's 2. There's 4. So 4 and 1 gives us 5, but this number right here identifies it as a -5. Now, I'm not sure if you can get into this figure here to do the executable file, but it is nice if you can see it. And it does a pretty good job of it in showing you how the digitation works. So, any questions on PCM? Quantizing, you had sampling, quantizing, and encoding. That's how it gets to the 8-bit code. So you're taking an analog signal, and by the time it all comes out, you have a digitized signal. That's how your PCM works in the PRIC 150.
Do we need to know how to decipher the binary code from the quantization?
No, you just need to know that you got 8 bits. On the 8th bit, identifies whether it's above or below the 0 line.
Copy that.
So, Roundsley, you there yet?
Yes, sir. I was told that that you called on me earlier, but I was in the bathroom, so sorry about that.
You know that you can text us, just down in the chat, hey, I've got to go to the bathroom, and I would have waited.
Okay, sorry, sir. I'll do that next time.
Yeah, that goes for everybody else. If you got to go, just, hey, drop a little chat down in the chat line. You'll be good. We just, because I was asking you a question. And it didn't make you look good, that's for sure. So,
yes, sir.
Now that you're back, what corrects for quantization errors?
Whenever it would automatically, I don't know the exact word, but say if you have something between a line, then it will, is it quantize? Is that what it is? Uniform quantizing.
Okay.
Non-uniform.
Okay. The one way to look at what corrects for quantization errors is non-uniform quantizing. And that's what I was trying to emphasize earlier. The non-uniform pushes those lines closer so you don't have the rounding errors. With uniform quantizing, you have a lot more quantization errors. Does that kind of help you out a little bit?
Yes, sir. I was trying to think of how to say it, but I couldn't find words.
Yeah. Non-uniform quantizing helps correct for most, notice that word, most quantization errors. You'll get it. And if you guys need help, I am normally on Discord from about 6 o'clock to about 6, 7, sometimes 8, 9 o'clock at night, you can send me a, hey, I need some help with this. To include, during the weekend. Now, the reason I say that is I'm not normally on the RF site, but I have a couple of servers that I go to when I'm playing World of Tanks. So it will pop up. Just, you might not see it for a couple hours, but I will answer you back. So again, if you guys are having problems with this, please, for the love of God, text me, chat with me. We can go into a room and do a voice chat, or I can pull up some slides or give you a little bit more in-depth on this, okay? Please. I don't want you guys to fail. I want to help you guys. All right, so next up, we got something called frame period. Remember back in the first part of this, we were talking about what a framing bit is? Well, we also have something called framing periods. That is how long it takes to sample from channel 1 to channel 24. Now, the reason I come up with channel 24 is because most of your standard multiplexers now come with 24 channels. That's what they're going with. Even though I've dealt with the SEC 100, which is 16 channels, and it will come into play when you are trying to figure out not frame period, but what's called pulse modulated sample period. So first of all, let's take a look at frame period. The definition for frame period says the time it takes for one frame to occur. This is based off of the sampling rate. Now, most of our multiplexers are doing 8,000 frames a second, or 8,000 frame periods. So what is a period? So one of those is we're going to take the reciprocal of 8,000 for that sampling rate. And in our case, when you do that, it comes out to 0.00125 seconds. In our case, it's 125 microseconds. That is a frame period. Time it takes for one of those to happen. Go ahead.
Is the 8,000 standardized regardless of how many frames you have?
Well, that's what we go off of, and that is what your standard multiplexer is going off of. It may change over a period of time. Again, this is, like if I was to do frame period for the SEC 100, it would be different because I think that one does... Oh, geez. The sampling rate is different on that one. I want to say it's like 6,000. I could be wrong. It's been a long time. They phased that out about 6-7 years ago.
Okay, so, but for the purpose of what we need for the course, 8,000 is our standard and our career, basically.
Correct.
Okay.
Yeah, I don't think you're going to be having to develop any cut sheets, but stranger things have happened. This is to get you familiar with what a frame period is, and it's a mathematical equation. Will we have you do a mathematical equation? The answer is no. We just show you that this is how we get it. So frame period, 24 channels, it's taken 125 microseconds. That's how long it takes. So the next one's called PMSP, pulse modulated sample period. So 24 channels in this space. Now I want to know what one channel, how much time it's taking to sample that. So what we do is we find out how many channels are in that frame period and take what we found out for what was factored as the frame period and divide it by the number of channels. In our case, we have 24 channels. That's what we were figuring on. So we've taken that 125 microseconds, divided 24 into it, and the time it takes for one channel to happen for its sampling is 5.28, and I think there's a lot more numbers that come after it, but it's like 0.00, 3 zeros, 2 more zeros, and then 528, and some change. So we just classify it as 5.28 microseconds. That's how long it takes for one channel to do its period or pulse modulated sample period in there. Time it takes to sample one channel in any given frame. So if I wanted to check channel 3, it's still going to give me 5.28 microseconds. Channel 10, 5.28. When I factor in all 24, it's going to give me 125 microseconds. So frame period is large. PMSP is one channel. So large versus small. And there you have it. We've gone over general multiplexing terms, data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, and last but not least, the beautiful and wonderful PCM of Audacity. Questions? Wow. You guys are a lively class.
Do we need... Oh, sorry, not do we need... Hang on. What would be the purpose of looking at a specific channel inside a frame?
For example, if you are programming, in other words, you're going to tell what that one channel can have. In other words, let's say 64K. You need to know what is its use going to be. Is it going to be VoIP? Well, yeah, how many microseconds am I going to have to do that? You know, if I'm going to come with a lot of data, which is isochronous, I might not want to give 64. I might want to do 128. Will you ever do that? The chances are highly, I would say rare. Back in the day,
we maintain the radios. We don't program the radios.
Exactly. Well, it's getting to the point now where we're dealing with radio over internet protocol, so this might come into play for it. And it depending on your multiplexer and what it does. So that's the internals of your multiplexer. So if you're having to develop some of this, let's just say that you went to, I'm trying to remember the doggone thing that, you know, they tried to recruit me up in, I think it's North Carolina, where we were doing a lot of experiments with radios to include radio over internet protocol. You would probably have to understand some of that stuff in order to do it. Again, it's going to be a rarity. I guess that's the best way I can explain it. You just need to be familiar with the basic facts of it. Hey, well, I know that there's a frame period, how much time it's going to take. I know there's pulse modulated sample period because I might need to know how long it's going to take to sample that one channel. And if I'm having a problem with it too, I could probably find it on when you do the GUI for NSM, and you're doing, along with the NSM, you're also doing what's called the BERTs. If it's throwing an error, you might have some issues with the timing there. I'm just saying. Any other questions? I know it's a wealth of information. You're going to have to sit back and regurgitate it later on. Start working on your homework. We'll go through that probably Monday after everybody's done. I'll take a look at, I'll get with you this afternoon as to a really good time where everybody's happy with. Again, I can do this after 4 o'clock because I'm here till 6. My time is supposed to be from 8 o'clock to 6 o'clock, but again, I'm early bird and late person. Any other questions?
Mr. Meyer, I have a question.
Sure.
Do you actually want us all to turn in the answers for the review questions to you individually, or we'll just go through it as a class?
I would like to go through it in the class. So I'm trying to figure out a way that I can see that you're doing the work, but not having to question why you weren't doing the work. So going through it in class, sometimes we get people that they won't answer a question because they're unsure. And I'd rather have that as being able to identify, hey, we need to talk about this a little bit more. So please do the work. You're supposed to be doing the work, by the way. And if you're running across the question, I'm going with the, excellence in all we do, integrity. That's the big one. I'm going on your integrity that you are going to go and do that homework. And if you have questions, you're going to chat with me or text me or whatever it is on Discord that you're having problems with this, and I'll steer you in the right direction. So the big thing is integrity. And I'm going to leave it up to Tech Sergeant Kennan on if he wants to check it or not. I personally think that you guys, this is in your ballpark. If you don't do the work, it's going to show on that test. It will show on the test.
Does that also apply to the worksheets we're doing? Just do them and then we'll discuss.
Okay. The way I instruct things is those worksheets are totally up to you. They're used for guidelines for studying.
All right, sir. Also, I already managed to repair that one file that was giving me trouble. So as of right now, I have all the worksheets that I need. So
okay.
Anything else? Thank you, sir.
And if you want to send them to me, please do, and I can tell you if they're correct or incorrect and send them back to you.
Yes, sir.
And that goes for everybody else. If you're questioning about the handouts that they have, I do not have a problem in taking a look at them for you. I'm just not a big fan of them because that's a lot of work on both your end and my end. Again, this is a college course. A lot of it is on you. I will help you for whatever questions that you are having. So please ask. I'm easily accessible. Ask anybody in this Discord channel. All right. Any more questions? Spore, you're good to go, by the way. I thought you were a Block 7. So I'll figure it out. I asked the ISs about that. So you're good to go. Go ahead there. I'm waiting on you to chat there.
I was just going to ask if we're meeting back at 1 o'clock.
Yes, we are meeting back at 1 o'clock because we got to go through objectives 1 Charlie, 1 Delta, and 2 Alpha, and then I'm going to go through the tech manual with you. So when you get into the NSM lab on Monday, you have an understanding as, oh, I just saw that, hey, on the GUI here, we talked about that. So that way you're kind of quasi-familiarized with being able to walk in that lab and doing what you need to do and getting out of there quicker.
Makes sense.
Are you performing the labs?
Am I? Negative. I am in a high-risk group.
Copy that.
Yeah.
Can you repeat what you told me, sir? I misheard because it was glitchy.
You're good to go.
You're good to go. You don't have to stay. I was under the impression that you had failed Block 7 and you were coming back through. So Sergeant Kennan has set me straight on that. And again, I will do my best. I've already put out the IS messages to why the test scores were not put in, and I will take a look prior to coming online at 1 o'clock to see if they've been put on, to check your scores out. All right? And if there's no other question, you guys are free to go. Go have a nice lunch, sit back, relax, and we'll see you at 1 o'clock, okay?
Yes, sir.
All right, you guys have a good one.